brought to you in association with Euresys and IMVE Tech Software. My name is Matthew Dale. I'm on the editorial team of Imaging and Machine Vision Europe, and I'll be your host for today. Our speakers will be exploring some of the key deep learning tools currently available for machine vision, advising on how to overcome the challenges associated with their integration and deployment across a variety of industries and applications. They'll be identifying where exactly deep learning can deliver operational benefit while offering guidance on how to select the right deep learning tool based on the vision application at hand and the materials or objects to be inspected. Fine, excellent.
Okay, hello everybody. I'm Antoine Lejeune. I'm the engineer in charge of the deep learning tools here at Euresys. And today I'm going to talk about our data-centric approach that we think can help you manage your deep learning project from annotation to deployment. So this is today's table of contents. I will start with a very quick introduction about my company, Euresys. Then I will also try to give an overview of the main advantages and drawbacks of deep learning algorithm and compare them to traditional rule-based image processing. I will also give an overview of the deep learning algorithm that we propose and how you can select them for your application. Then in a second time, I will present the workflow that we've implemented in our deep learning tool and how it can help you to manage your image, your models, and deploy your models into production. Finally, I will try to showcase how this tool can help you improve your data quantity, your data quality at various steps of the workflow. So Euresys is a machine vision component company. So we offer three types of products. The one we are the most known for are frame grabbers, but we also offer IP cores. And we also offer machine vision software. This is the reason I'm here today. So the machine vision software that we offer is called the OpenEVision library. And within this library, we have now several deep learning algorithms available. And we have also a companion tool that helps you annotate and train all your deep learning model for OpenEVision. So we are based in Belgium, but we have R&D offices in Germany and in Belgium. And we have also, of course, sales and support offices all over the world. So let's get into the subject. So how can deep learning bring you operational benefits for your inspection application? So here I identify two major advantages of deep learning algorithm. The first one is performance. Given enough data, again, good enough data, usually a deep learning algorithm will outperform a traditional rule-based machine vision algorithm. And it can even be as good as a human inspection, or sometimes be better than a human inspection, at least more regular and more consistent. Also, from a certain point of view, deep learning application require is kind of low code. By that, I mean that the part in your application that will do the deep learning inspection will require a few lines of code compared to traditional rule-based image processing algorithm. So you can develop your application faster, it will be easier to maintain. And also, thanks to the fact that all the complexity of a deep learning algorithm is contained within a model file, you can have a single program that you can deploy with different models and models that you can update to take into consideration new use cases, new types of defects, for example. So when would we rather use a deep learning algorithm compared to a rule-based image processing algorithm? Well, there are a lot of criteria and a lot of trade-off to take into account to make this kind of decision. Here I have highlighted a few of them. So typically, a rule-based image processing algorithm will be faster. Its processing speed will be higher. And also, it will be more interpretable. By that, I mean that you exactly know why your inspection algorithm will give you a certain decision, because you have encoded, your vision software engineer encoded all the rules in your program. With a deep learning algorithm, you know that on average, your accuracy will be a bit better, but when you get a decision from the neural network, it can be quite hard to say why this decision was made. And it can be a problem in some industries. But on the other end, deep learning algorithms are proficient on complex data with complex texture, complex patterns, when there is a lot of noise, when there is a lot of inner variability in the images. So, for example, deep learning algorithm works very well on natural products, for example, the waffles and coffee in this slide, but it works also very well on manufactured objects where defects are quite complex, for example. Also, for example, if you already have a lot of images for the problem that you want to solve, this put weight in favor of using a deep learning approach. Because if you have already a lot of good images, you have already done the first step towards developing a good deep learning application. So for what can you use deep learning? So here I have categorized the deep learning algorithm for image-based inspection in 3 big categories: classification, segmentation, and localization. So for classification, we want to predict for each image a category. So it can be used for defect detection, product recognition. It will usually be one of the fastest of the deep learning algorithm. We have segmentation. In this case, we want to predict a class, a label for each of the pixels of the image. So you get more information about your image using segmentation. But of course, it will be slower and it takes more time to annotate a data set for segmentation. So we have instance localization. In this case, we are trying to predict instances. And by that, I mean an area of the image that correspond to an actual real-world object or pattern or stuff, something like that. So the instance can be represented by a point, by a bounding box, by an oriented bounding box. We can have optional segmentation of the object. But the main advantage of this type of algorithm is the ability to cope with overlapping objects. And so it's very good for applications such as package verification, counting, but it can also be used for defect detection, for example. And so which of these algorithms to use for our application depends also on a lot of different criteria and trade-offs. For example, if you have a strong execution time constraint on your production line, you may want to go towards classification because it will be faster, even at the cost of trying to get a different acquisition method, trying to capture your image differently, such that your data set better fits this type of algorithm. So now let's talk about how exactly can we put that into practice and develop deep learning models with Euresys tools. So we've tried to develop a kind of iterative workflow based on trial and error, which is data-centric and data-driven. So here in the little drawing, we usually start by getting images. Then we annotate, we can configure the tool and the training parameters, we train a model, and then we need to evaluate the results. And according to if they are satisfactory, we can go to deployment. Otherwise, we need to start over and try to improve our data sets, maybe improve the model. And so at each step, either you generate data, for example, by annotating images, or the tool will generate data, for example, by computing results with the model that we have just trained. And so having a tool that properly tracks all the data that is generated across all the steps of the workflow is really useful to help you create your deep learning models. So the tool that we have developed here at Euresys is called Deep Learning Studio. It's completely free. You can download it right now on Euresys website. And it implements the workflow I just talked about using tabs. So for example, here we see the dataset annotation tab, which is where you will add images and annotate your images. Then the next few tab is where you configure the deep learning algorithm and the training parameters. Then we have a tab to validate the result of the tool that you have trained, check the results for individual images. And we have also tabs that will help you find the best deployment and execution settings to maximize speed on your specific images and hardware. So this is a benchmark tab. So again, Deep Learning Studio will help you track all your projects, help you annotate, track your annotation, which image you have already annotated. It will manage and track all the models that you have trained. It will allow you to compare and evaluate all the models. And as I said, you can also benchmark each of the models that you have trained with various different execution settings to find the fastest way possible to execute your neural networks. And so now, to end this presentation, I'd like to showcase how Deep Learning Studio can be used at various steps of the workflow that I presented to improve data quality and quantity. So, as Christian said in his presentation, data quality and quantity is really paramount to developing a good deep learning-based application. Without good and enough data, you will not get good result even with the best model in the world. So by data quality, I mean, for example, well-defined categories, good, consistent, and precise annotation. And in Deep Learning Studio, we try to give you the tool to maximize this quality. For data quantity, it's simply having enough images to correctly represent your problem. It's inner variability. And it really depends on your particular application and on the model, how much data you will need. So our goal here at Euresys is to implement algorithm that will minimize the amount of data that you need, but you will still need a certain amount of it. So the first place to look to improve both data quality and quantity is, of course, the annotation step. And this is why that we have introduced a few years ago an AI-assisted annotation tool. And so it makes annotation here for segmentation much faster. And so for the same time budget, you can annotate more images. And also it will make your annotation more consistent than a manual labeling, which can also improve the training of the deep learning models. Another step in the workflow to improve both the quantity and quality of your data is the analysis of results. For example, by looking at where a previously trained models makes mistakes, you can find bad annotation. So images for which you have assigned the wrong label, for example. You can find ambiguous labels. So these two has problem with data quality. So you need perhaps to reformulate your problem and reformulate all the categories that you want to recognize for your problem. You can also try to identify subsets of images that are quite similar, which are all wrongly predicted. And so you might need to add images that look like them to your data set to increase the learning for this type of images. Also, in Deep Learning Studio, you do not need to annotate all your images to train. You can add a lot of images, annotate a few of them, try to train a first model. And when you are looking at the result for this model, you will be able to quickly go to the result for all the images that are not yet annotated. So you can review the prediction made by this first model that we have trained. And if the prediction are good, you can use this prediction as basis for a ground truth annotation. So this will help quickly increase your data quantity, and in the end, it will improve your models. To conclude this presentation, deep learning algorithm will always require good data in enough quantity. it's really important to have good tools to manage this data in your project. And we believe that the tools that we develop here at Euresys and the data-centric approach will greatly help you to manage and develop your deep learning application. Thank you very much.
Excellent. Thank you very much, Antoine. So we're going to move straight on to the Q&A session there. We had a couple of questions have come in asking about the quantity of images. I think you mentioned there there's ways of, if you improve the data, you can reduce the amount of images. But I suspect the answer is it varies, but perhaps a ballpark figure of how much data, how many images are required to train something like this. We've had a user come in that says, for example, if they've got a production system that's quite reliable, it's not creating that many defects. If the process is quite reliable, is there a way to tackle this issue? So perhaps, yeah, a bit of an overview of how many images are required to train something like this.
Well, we've had some cases where less than 100 images were sufficient to produce good results, but with less than 100, it's quite hard even to have good metrics, good estimation of the accuracy. So usually 100 images is quite a minimum if you want to have a robust estimation of the performance of the model that you get. Also, for the cases where defective products are very rare, and it's very hard to get images with defects, then you may use, for example, unsupervised segmentation, which are deep learning algorithms that trains only on good images. And so you don't need to have examples of defective product to train. Of course, you really need to have some defective images to check if the model is correctly able to recognize some of the defect that you have.
Just going off that then, are there, would you say between those two types of learning where you're using the corrected images versus using perhaps just defective, is there one that's perhaps more reliable than the other? Would you always recommend one over the other, or can both be as reliable as each other?
Well, it will always be more reliable to be able to construct an explicit model of what you want to detect. So if you can have a lot of examples of what you want to detect, it's always better to use supervised training, and it will give more better result in general.
Excellent, thank you. What else have we had come in? So somebody's asked whether it's possible to use your deep learning tools, run them on embedded platforms. Is that perhaps something you'd like to answer?
Yes. Yeah. So the software that presented Deep Learning Studio is the tool that creates the models. And then to make it run in your application, you need to use the OpenVision library that works on Windows, Linux, Intel, ARM. And so you can really deploy a model on embedded platforms. Of course, deep learning algorithms sometimes require a lot of processing resources. And so you might need to use embedded platform with GPUs, such as NVIDIA Jetson platforms or AI accelerators and stuff like this to make sure that your images are processed fast enough on such platforms.
Excellent. And then perhaps just quickly, because we need to move on to our final presentation in a second. Someone's just asked about the licensing model of your deep learning tools. Perhaps you could take us through that quickly.
Yeah, as I said in the presentation, Deep Learning Studio is completely free. So you can directly annotate your image, train new models, and analyze your results. It's when you want to deploy, well, you will have to buy a runtime license to deploy your model into production.
Brilliant. Thank you very much for answering those, Antoine.